Okay, good morning and welcome to class today. We're looking at chapter 2 still on chemistry here in A&P. If anybody has any questions on anything, this is a good time to raise them. So if you have any questions on anything at all, that's fine. If you want to send me an email, I'll get back to you as quick as I can on that. And so we're just about done with chapter 2. I don't think we'll finish it today, but because in the first class I got almost done. So we'll definitely wrap this up by Thursday, and we'll finally be done with Unit 1. So if you have any questions, otherwise I'm going to go ahead and start. And let's get into, I want to get that far with it. Back up here. I want to start us off with lipids. I think we were done with the carbohydrates, and it's not going to hurt to start the lipids again. So we had finished up talking about the carbohydrates. The carbohydrates are the sugars. They show up as sugars and starches, things we eat, the pastas, the breads, the sugar in coffee, the sugar in our foods, sugar in the fruit that we eat, and starches. Carbohydrates show up as monosaccharides like glucose, which is what our body uses, disaccharides like sucrose, which is what we use for sweetener in coffee, the stuff that comes in the white packets and things like that. And then, of course, the polysaccharides like glycogen, which is what we store glucose as well as starch that plants store, and we eat the plants and get the starch. And of course, we have the fibers over here too, the cellulose and stuff like that. Okay, now moving on, lipids. Similar makeup as carbohydrates, carbon, hydrogen, and oxygen. But it's not always in a 1 to 2 to 1 ratio like it was in carbohydrates. And we occasionally see phosphorus thrown in there too. The fats are not soluble in water. We know that. If you mix oil and water together, or like, in oil and vinegar, for example, which is the vinegar is mostly water, the oil floats on top. It does not mix. The lipids, if I say fats, I mean lipids. Lipids occur in 4 categories. The triglycerides, or what we call the neutral fats. This is the stuff that shows up in our blood. This is what we worry about, our triglyceride levels. What is the fat level in our blood? It's also how we store excess lipids in our bodies as fat. The phospholipids are exactly what it sounds like. It is a lipid with a phosphate group attached to it. We find this in every cell in our bodies. It forms the cell membrane. We have what's known as a phospholipid bilayer of these molecules. Steroids show up derived from cholesterol. We have steroid-based hormones like the sex hormones, for example, testosterone and estrogen, as well as the different hormones from the adrenal glands that control glucose levels in our body and control our ability to respond to stress and things like that. And then we have the eicosanoids. The eicosanoids are a type of fat lipid that we use to help control inflammation in our bodies. So, again, I said this before, I'll say it again. If it's a fat, if it's a lipid and it's a fat, it's solid at room temperature. Or rather, a solid lipid is a fat. A solid lipid is a fat. Butter is a solid lipid. Animal fat is a solid lipid. The lard is a solid lipid. Okay. Fats when they're called fats when they're solid, and oils when they're liquid. Animal fats are solid lipids. Animal fats are always solid at room temperature. Plant fats are always liquid at room temperature, and we call them oils. Fats and oils. Fats are solid, oils are liquid. Oils come from plants, fats come from animals. Fats are solid at room temperature, oils are liquid at room temperature. They're all made of 3 fatty acid chains, 3 molecules of carbon and hydrogen linked together, maybe 20 or 30 carbon atoms linked together in a long chain with an acid group at one end. And these are the fatty acids, and they occur in 3s. And they are attached to a molecule, a 3-carbon molecule, what we call glycerol. Glycerol is an alcohol. Anytime you have the OL ending, it means it's an alcohol. Glycerol is an alcohol. Ethanol, the alcohol we use in added to our gasoline, or the same alcohol that we see in beer, wine, and mixed drinks, all have the OL ending. So it's ethanol. So glycerol is another type of alcohol, and glycerol is covalently bonded to 3 fatty acid chains to form the triglyceride, 3, so 3 fatty acid chains. The whole purpose of triglycerides is for storage of energy, because lipids have a great deal more energy than carbohydrates do. 1 gram of lipid, a gram of fat has 10 calories of energy. A gram of carbohydrates only has 4 calories of energy. So there's a great deal more energy stored in a gram of fat than there is in a gram of carbohydrates. Now, if you look at the calorie makeup of any food, for example, you read the food label, and if it has 4 grams of carbohydrates, it's going to have 16 calories. If it has 4 grams of fat, it's going to have 40 calories. There's more stored energy in the lipid than there is in the carbohydrate. So energy storage in our bodies, we store lots of energy in the adipose tissue cells. We store fats. We store the neutral fats in our adipose cells. And so that's a great energy reserve. We also use it for insulation. The layer underneath the dermis, the hypodermis in our skin, contains adipose cells with fat inside. That keeps us warm in the winter and cooler in the summer. It is to insulate us, and it also protects us. And it protects a lot of organs that have no other protection. Our kidneys, for example, set high in the back wall of the abdominal cavity, right underneath the diaphragm. The only protection they have is they're embedded in a layer of fat. That's it. There's nothing else to protect them. There are no bones around them. Their ribs don't offer any true protection to the, even as they extend down a little further there, they don't offer any true protection to the kidneys. So this is what, let's see, question. Yes, my YouTube channel is, that's the name of my YouTube channel, WG Sprout. So let me send it out to, there you go. I hope that helps. So Now, has everybody, I hope everybody's been getting the link. I send out the link every day for the lecture and for the lab. And you should be able to, if the link works, it should take you right to it. So anyway, the triglycerides, 3 fatty acid chains attached to a 3-carbon glycerol. This is the glycerol here, 3 carbons, it's an alcohol. It has 3 hydroxyl groups attached at the end here. That's the OH groups. And here is the fatty acid chain. This group out here, this little area here, that's the acid group. Good. Okay. So, and not to try to go over any organic chemistry today, but the C double bond O with the OH group is always an acid group. Anyway, this is a fatty acid. It has an acid at one end, and then it has a long chain of carbon atoms with hydrogens here, here, and here, and they are bonded to the 3 carbons of the glycerol. So that gives us our triglyceride right here, our neutral fat, meaning it doesn't have a charge either way. Carbon, carbon, and carbon, a chain, a fatty acid chain here, a fatty acid chain here, and one here. All balanced, all neutral. This is an acid because of the acid group here. If you ever were to take organic chemistry, then you would see what the acid functional group is all about. But you don't need to worry about that for today. I took organic years ago as an undergraduate, and to this day, no one has run up to me and said, hey, what's the functional group on a fatty acid? Has never happened. So I'm ready, but no one ever does it. So anyway, the glycerol and the fatty acids combine to give you the triglyceride. And there's a lot of potential energy stored in this big molecule here, in the triglyceride. That's why you have 10 calories of energy per gram, as opposed to only 4 calories in the carbohydrates. Now, if you are a lipid, you can be a saturated fatty acid. If you are a neutral fat, you're a triglyceride, you can be saturated. That means that all the carbon atoms are linked together with single covalent bonds to all the other carbon atoms and the hydrogens. So every space that can have a hydrogen atom has one. It's saturated with hydrogens. So in your chain of carbon atoms, you have, every carbon atom is going to be linked to to 2 other carbon atoms and to 2 hydrogens, except the one in the end, it'll have 3 hydrogens. And so the total amount, the maximum amount of hydrogen atoms are present here. It is saturated. And the fats that have this are going to be the animal fats. The fats that are solid at room temperature, the butters, the lards, the animal fat that you trim off of meat, beef and chicken and pork, that kind of fat is all solid at room temperature. So, because it is a saturated fat. This is what a saturated fat looks like right here. A single bond, single bond, single bond, all the way across, and every space filled up with hydrogen. An unsaturated fat is a little different. An unsaturated fat has a double bond somewhere in the chain between the carbons. So instead of sharing 2 electrons, we're sharing 4 electrons at the double bond. The double bond causes the chain to assume a different shape. It causes the chain, the fatty acid chain, to bend at the double bond. It bends and twists and kinks, and it even rotates around the double bond. Sometimes it can even pinwheel around the double bond. And this doesn't allow the fatty acid to stay solid at room temperature. In fact, the fatty acid now with the double bond in there causes the entire triglyceride to be a liquid at room temperature, simply because we don't have every hydrogen filling up every space. We have a double bond in the middle here. So to summarize this, fatty acid chains are about up to 20 carbon atoms long. They're all held together with single covalent bonds. If it's saturated, all 20 carbon atoms are held together in place, attached to each other with single covalent bonds. There are single covalent bonds attaching the hydrogens to the carbons. So every carbon has the maximum number of hydrogen atoms it can have. If it's saturated, if it's unsaturated, it has a double bond in there. And so it's missing a couple hydrogens because of the double bond. If it's unsaturated, it has one double bond. If it's polyunsaturated, a term that you've also likely heard, you heard unsaturated, and you may have heard polyunsaturated. Polyunsaturated fatty acids have more than one double bond, at least two, maybe more. And the chain will always bend. The chain will always bend and kink and twist at the double bonds. Saturated fatty acids are solid at room temperature thanks to van der Waals attraction. Remember, van der Waals was that fourth type of chemical bond. It has 1/100th the strength of a hydrogen bond. It occurs when electrons moving in orbit around their nucleus of various molecules randomly group together on one side of the molecule or another and create a very slight positive or negative charge on that side of the molecule. And that attracts the adjacent molecules to it. The adjacent molecules are pulled together and they're held together in place momentarily. And then they let go because the charges shift back, and it continues over and over and over again. Because these fatty acid chains are so close together that if the electrons shift and create a slight positive or a slight negative charge, the chains clump together. Van der Waals attractions between the fatty acid chains is what makes fats solid at room temperature. Unsaturated fats with their double bonds and the kink that occurs in the bond, in the chain, or the multiple kinks, for example, those don't allow van der Waals attraction to occur. So van der Waals attraction is not going to happen if the chain is bending and twisting. And so your plant fats don't get van der Waals. They don't become solid. They aren't solid at room temperature. They're a liquid. They're an oil. And they're an oil because there is no van der Waals attraction pulling them together. Simply because their chains have double bonds. Plant fats are made up of unsaturated fats. They're not made up of saturated fats. Plant fats, all plant fats are in a liquid form because of their double bonds. And so they're liquid because of the double bond. The double bond prevents van der Waals attraction from occurring, so they can't clump together. They can't be a solid. They're a liquid. The unsaturated fatty acids have a double bond present. All plant oils are going to be unsaturated. They're not going to have all the hydrogens there. They're going to have their double bonds. And good example, olive oil, or corn oil, or canola oil, or sunflower oil, or safflower oil, or just plain old vegetable oil, which is a mixture of corn oil and something else, or maybe just another name for corn oil. Go to Food City or Kroger and look at all the oils in the aisle, in the baking aisle, and you can start reading labels and pretty much you're like, I don't know which one to get. They're all about the same. they're all going to be about the same. My wife prefers olive oil over anything else, but they're all, they're all pretty much about the same. They all have lots of unsaturated fats and no saturated fats in there. So anyway, unsaturated fatty acids are liquid at room temperature thanks to the presence of double bonds, which prevents van der Waals from occurring. Now, two terms here, trans fats and omega-3 fatty acids. Omega-3 fatty acids are the heart-healthy fatty acids because they are unsaturated. It sounds like a circular logic, but the omega-3 fatty acids are the type of fatty acids that are unsaturated, and they are less likely to cause heart disease. The trans fats are fatty acids that have been modified and they become unhealthy. Let me explain how that happens here. Okay. So here, let's watch this. This should be interesting.
Butter, lard, margarine, and salad.
Right, they have 10 calories per gram as opposed to 4 calories per gram. So you'll notice that these molecules here are all saturated. These are saturated fats. And this would be a solid at room temperature because there is no double bond in any of the chains that would cause the chain to kink and twist and pivot and prevent van der Waals. This particular fatty acid, this is a fat because it's experiencing van der Waals attraction. Thank you, we just saw that. Okay, now, unsaturated fatty acids can be unsaturated with one double bond, or they can be polyunsaturated with many double bonds. Here is oleic acid, a monounsaturated fatty acid, one double bond here. No hydrogen, no hydrogen. Compare that to even one of these smaller smaller saturated fats. This is butyric acid. 3 carbons in the chain. There's the acid group at the end. It's a solid fat. It will have you'll have these lined up, and it will, because of van der Waals attraction and no kinking, it will be a solid fat. So find it in goat butter, believe it or not. Linoleic acid, polyunsaturated because it has 2 double bonds here. It bends here, it bends here. And it prevents any van der Waals attraction from occurring with the other fatty acid chains. A liquid at room temperature. Both of these, oleic acid and linoleic acid, are going to be in liquid fats, in oils. However, we don't like to leave things undone. And so the food industry has found that you can take unsaturated fats and saturate them through a process known as hydrogenation. This is not a bad thing as far as it goes. Oils can be hydrogenated back to a solid. If you've ever seen Crisco shortening, Crisco is a alternative to using lard for baking. Crisco shortening is nothing but corn oil that has been hydrogenated. The corn oil has had hydrogens added to it. The double bonds are broken, and we now get a solid. If you open up a can of Crisco, it is white. That's what it looks like. That's what a hydrogenated fat looks like. It's a white substance. Crisco has to have salt added to it for any kind of flavoring, and it has might have I don't know, some other additives in there for stability or appearance, but it has become hydrogenated. We use Crisco as shortening. You make biscuits with Crisco. You make pastries with Crisco. You make pie crust with Crisco. Crisco, as a shortening, works to make bakery shells, pie crust biscuits, since we've had light and fluffy, or at least light. You don't want a fluffy pie crust. The fat, the shortening, as it heats up when it's baking, gives off carbon dioxide gas. That causes the pastry dough to separate into layers. And the more layers you get, the lighter and tastier the crust is. A pie crust should be light and flaky. Shouldn't be, chunky. Biscuits should be light and flaky. Without shortening, your pie crust is like a. Let's put it this way: without shortening your pie, you can't tell your pie crust from the pie pan. A biscuit made without shortening is like a hockey puck. They're solid, definitely solid. So the shortening allows this to happen. Well, now Crisco shortening was developed as an alternative to lard. Lard is rendered animal fat. It's melted down and stabilizes, and then it's put in cans as animal lard, and it's used in baking. The best bakeries use lard to make their pastry shells, to make their pie crusts, to make whatever, because it does a better job of making the pie crust light and flaky. Now, and it comes down to how many biscuits do you eat on a daily basis or a weekly basis? How many pie crusts do you eat on a daily or a weekly basis? How many pastry shells do you eat? How often do you eat shortening or eat Crisco or lard? Well, it just depends. Some people like to have biscuits and gravy every day, so you're getting your extra shortening through that. The process of adding hydrogens to the unsaturated fat hydrogenation has a drawback. It can produce a compound known as trans fats. Now, a trans fat is a triglyceride that has one chain or more turned in the opposite direction. See, we have trans fats and cis fats. It's all about the molecular structure. In a trans fat, the one or more of the chains is turned in the opposite direction than the rest of them. The cis fats all have the chains going in the same side. And we use cis in chemistry. If you ever take more, general chemistry or even organic chemistry, you'll learn that there's cis and trans forms of molecules all the time. There's no right or wrong. There's no good or bad. It's just the shape that some of them assume. So in the case of fats, the trans fats, one or more of the chains turns in the opposite direction from the rest of them. Maybe they all turn in the opposite direction. Trans fats, it turns out, whether they're naturally occurring, which they do occur naturally, or they're made through hydrogenation, are generally, have been considered a really good advantage to food because it stabilizes their shelf life. It gives them greater shelf life for storage or on the shelf at the store. It helps maintain a constant texture in the food product. It also helps to maintain the same flavor because the food industry is all about shelf life and a constant flavor and a constant texture. You want your Oreos to always taste the same. You want your Fig Newtons to always taste the same. You want your cereals to always taste the same. one of the great things that McDonald's did in the food industry was they ensured consistency. So a quarter pounder in Tennessee tastes exactly the same as a quarter pounder in Nebraska. You go anywhere in the country and a McDonald's burger tastes exactly the same. Before that, it was all random. Everybody's burgers tasted differently. And they were all cooked differently with consistency. And that's what the food industry is all about. So trans fats are not necessarily a bad thing. They maintain stability at a lower temperature than the cis fats. The cis fats are usually your oils. And they are going to, the cis fats will, are only solid at higher temperatures. Trans fats are solid at lower temperatures. So they can give us great stability. However, and of course we see it now here, for example, margarine. Margarine is a classic example of a hydrogenated fat. Corn oil, liquid at room temperature, hydrogenated, it turns into a solid. But margarine looks just like shortening when it's first manufactured. It comes out as a white lump when it's processed. Years and years and years ago, probably after the First World War, so probably well over 100 years ago, margarine was sold as a butter replacement. But because the dairy industry was so powerful at that time, if you were going to buy margarine, you had to buy it with a dye pellet and a flavoring pellet, and you had to mix it together yourself because it came out looking white, just like it did in the packet here. You had the flavor, as I said, the color berry and the flavor additive. You mixed it all together, and then you had your yellow margarine that looked and tasted like butter. Now we have all sorts of margarines on the shelf that are all hydrogenated oils. Country Crock, I can't believe it's not butter. I think this is Land O'Lakes margarine here. Can't quite, I think it's Land O'Lakes anyway. So lots and lots of margarines sold to look just like butter, as a butter substitute. And the only problem with margarine is that you've hydrogenated the oils, and to get it to taste and look like butter, you have to add coloring agents, food dyes. You have to add flavoring agents and a lot of salt to get it to taste good. And so it is very, margarine can taste very similar to butter. If you go head to head and compare butter to margarine, some margarines are so good you can't tell them apart. Others you can. Now, the question is, how much margarine do you eat on a daily basis? How much butter do you eat on a daily basis? Because it all comes down to moderation. Butter and lard and animal fat are not necessarily evil objects. Margarine, hydrogenated oils are not evil. It all comes down to how often you eat. So, how often do you have biscuits? How often do you have biscuits made with shortening or with animal fat? How often do you have butter on your potato? How often do you have margarine on your potato? It all comes down to moderation. Because there really isn't much, there aren't many food types that anybody would ever consider to be completely and unadulteratedly bad for you. It has to come down to how often do you eat it and how much do you eat at a time. Now, trans fats, as I said, are made have in the past been made in the process of hydrogenation. They also occur naturally like in dairy products and meat. Trans fats show up in the fats from animals, but you also can inadvertently produce trans fats through hydrogenation. Now, the problem with trans fats in our bodies is that trans fats increase the development of a lipoprotein, a fatty protein in our blood called low density cholesterol. It's the LDL, the evil cholesterol. It's a low density lipoprotein, LDL cholesterol, the bad cholesterol. You've heard people describe the bad cholesterol and the good cholesterol. What happens is when we eat fat and we convert some of it to cholesterol, we put that cholesterol in our liver. The cholesterol is sent out to the cells for use. I mean, we use cholesterol to stabilize the cell membrane. We use it to make various hormones. There's lots of uses for cholesterol. And we use the high density lipoproteins, the good cholesterol, to transport the cholesterol out to the cells. And that's great. And that's where it goes. And if when we want to get rid of it, the HDLs bring the cholesterol back to the liver for destruction. And that's good. We get rid of the excess we don't need. Low density lipoproteins transport cholesterol, but don't bring it back. And so it accumulates in the cell, in the tissues. Low density lipoproteins will transport cholesterol to the heart, to the brain, to the various blood vessels in our body. It will accumulate and start to accumulate inside the vessels of our bodies, blood vessels, forming a substance known as plaque, reducing the blood flow, and particularly in the heart and in the brain, and it contributes to the development of atherosclerosis, what we refer to generically as hardening of the arteries, which leads to heart disease or the possibility of a stroke or a clot in the brain. So a heart-healthy diet tries to avoid the LDL, the low-density lipoproteins, because that's going to be what allows cholesterol, excess cholesterol, to accumulate in the muscle, in the heart, and in the brain, and in the blood vessels. We don't want that. Trans fats, the presence of trans fats stimulates the production of these low-density lipoproteins. So we carry more cholesterol to those tissues and leave it there. So where are we getting the low-density lipoproteins? Animal products. If you eat a lot of red meat, you've already got cholesterol and fat embedded in that red meat. There's nothing wrong with red meat in moderation, but if you eat a lot of red meat, then you're bringing in cholesterol, and you're also likely have trans fats in the fat from that meat because it occurs naturally. And so you stimulate accumulation of cholesterol deposits in your heart and in your brain. You eat a lot of dairy products, a lot of dairy products, butter, ice cream, milk, lots and lots of these products. Excessive consumption of this. A lot of cheese. Many of us love cheese in all forms, whether it's on pizza or just cheese by itself, or a cheeseburger, or whatever. And so the cheese will also contain trans fats, and it will contain the fatty acids, and some of them are going to be trans fats, and they're going to, first of all, you're going to be bringing in extra cholesterol, and then you're going to be storing it in parts of the body we don't want. And so we see if we eat trans fats in any shape or form, we're going to be stimulating the release of cholesterol from the liver where it goes, because everything we eat has to go to the liver first before it goes anywhere in the body. Everything we eat goes into our liver to clean it up. Cholesterol is sequestered in the liver and then sent out to where it's needed. When we pick up all that fat and cholesterol if we have a high fat diet, we're going to contribute to health issues later on. Now we see, let me go back before I go on. We've seen advertising on TV about certain foods, are heart healthy. Yes, they don't have any trans fats. In fact, you can't get trans fats in any product that you buy except in meat and dairy, because they occur naturally. The food industry is prohibited from creating trans fats in peanut butter and in margarine and in shortening and anything that they would hydrogenate. But we still get them in, the meat products and the dairy products that we consume. So again, it comes down to moderation. We see advertising that says certain foods are even more heart healthy, like Cheerios. Cheerios is advertised as a heart healthy product, and that's a true statement. It has to do with the oat kernel. Cheerios are made of oats. The oat grain is ground up, and we eat Cheerios. They make Cheerios out of it. In fact, you may have seen advertising, seen them in the stores now. They have a throwback label called Cheery Oats, which was its original name. Anyway, the bran, the outer husk of the oat kernel will stimulate the production of the good cholesterol, the high density lipoproteins that will bring excess cholesterol back to the liver for destruction. And so the Cheerios advertise themselves as heart healthy, and it's true because they use oat and the oat bran. The oat bran, the husk of the oat kernel stimulates HDL production. Cholesterol is brought back to the liver. We destroy it, and it's a healthier food. And it's not just Cheerios. It's any oat-based cereal. Oatmeal, in its various forms, is a heart-healthy cereal. Any generic Cheerios knockoff, the Food City house brand, the Walmart house brand, those big bags of cereal that you find in the bottom shelf at Walmart, like a 5-pound bag of cereal. If they're oat-based cereals, then they're heart healthy too. All oat brand-based cereals do the same thing. It isn't just Cheerios, but they all work. They're all heart healthy because they increase the HDL levels and decrease the LDL levels. So that's actually advertising that is a valid statement. Okay, let's go on here. Now, where does all this fat come from in our bodies? The adipose tissue is our cells that simply store lipids. That's all they do. Adipose cells are not in themselves inherently bad. They're just a storage facility for lipids. When you eat something, when we eat anything, first of all, it all has to go to our liver. It gets absorbed, everything is absorbed in the small intestine and goes to our liver for what we call detoxification. Whether it's coffee or tea or milk or a cheeseburger or Cheerios or whatever, everything we eat and drink goes to our liver from our small intestine. It's cleaned up, and then and only then can it enter the blood supply. If we maintain a high fat diet or a high carbohydrate diet, let's say we have a high, lots of carbohydrates. Well, carbohydrates are broken down to glucose. Glucose is the sugar that shows up in our blood as blood sugar. And when our blood sugar goes up, we release insulin from our pancreas. Insulin tells our cells to open up special proteins that form channels in the membrane of the cell. We call this facilitated diffusion. You heard me talk about that in lab. Facilitated diffusion is just a specialized channel for glucose. Let glucose enter the cell. Glucose can't get into the cell because glucose is not fat soluble, but it can go through this special tube and get in. That's what insulin does. It tells the cell, hey, sugar levels are high in the blood. Let's bring it back down. So you bring in sugar. If you bring in a lot of sugar, the excess sugar is going to get converted to glycogen. If it's even more sugar, it's going to get sent to the liver to form glycogen there. Muscle cells contain lots of glycogen on their own, and excess glycogen's in the liver. It's stored energy. Glycogen is nothing but, lots and lots of glucoses linked together. And so we have stored energy there. If you have even more sugar, even more glucose, it moves into the fat cells and is converted to lipids. So a person who maintains a high carbohydrate diet will likely see an increase in the size of their fat cells as more and more sugar is converted to fat, chemically converted to fat, and stored in the fat cells. We call this lipogenesis, the creation of lipids. It happens. The more carbohydrates you take in than your body needs, the more that's going to get stored as glycogen, and what's left over is going to get stored in the fat cells. Case in point, I had a friend years ago who worked for the State Department, and she got posted to Paris to work at the embassy in Paris. Fantastic job. And she loved living in Paris. It was for a year-long posting. So at the end of the year, she discovered she had gained 40 pounds. She couldn't figure out why. And what would happen is when they would take their coffee breaks, and they were very adamant about their coffee breaks and stuff at the embassy, they would all go around the corner to this little bakery. Imagine that, a bakery in Paris. And they would eat breads and rolls with lots of butter every day. And all that excess carbohydrates started to accumulate. When you're working in a job where you don't get to move around a lot, so you have a rather sedentary position, you don't get to burn as many calories as you'd like. Turns out she was probably taking in about 4,000 calories a day and burning about 2,000. So those extra carbohydrates were converted to fat and stored in her adipose cells, and she gained 40 pounds. Now, it took her about a year to knock that off after she came back, because it was a lot of work to get that down. But the weight gain came from excessive amounts of carbohydrates. Our bodies will take it in, and we'll end up storing it in our adipose cells if we can't store it anywhere else. It's a great source of energy as long as we're drawing on it. But if we are not using it, we store it. Now, when we do need it, those same adipose cells can release the lipids and allow it to get broken down into glucose. And it's called the lysis, the rupturing of the lipid molecule. We call it lipolysis, lipo for lipid, lysis. Anytime we see lysis, we're dealing with the rupturing of a molecule, of a cell, of anything. Hemolysis is lysis of red cells. Lipolysis is the rupturing of fat cells. So we can store it in the adipose, we can take it out and break it down and release it for energy. Here we go. Now, okay, so those are the triglycerides. 3 fatty acid chains attached to a glycerol. It can show up in various forms there for us. Now, the second category are the phospholipids. Phospholipids lose one of their fatty acid chains and replace it with a phosphate molecule. And our cell membranes are made of these phospholipids. They look like the structure here. They have a head where the phosphate and the glycerol are located, and they have 2 tails, which are the fatty acid chains. And we say it's a phospholipid bilayer in the cell membrane. We have 2 of these, 2 membrane formed, both of which have the head, the round area, on the outside or the inside. So lining the inside of the cell at the membrane, you have the heads. Lining the outside of the membrane, you have the heads, and you have the tails in between. And this is very, very important. This is how all of our cell membranes and every membrane in our bodies are made this way with these phospholipids. The steroids, the third category, are all derived from cholesterol. They all have the same basic structure. They have 4 rings linked together, but they all have different functional groups. But they're all similar. Cholesterol and vitamin D. The vitamin D is embedded in our skin. When stimulated by ultraviolet radiation, we produce vitamin D from these receptor sites in our skin. The sex hormones, testosterone and estrogen, the bile salts that come out of our gallbladder, made in our liver and stored in our gallbladder. We break down fats in our small intestine with it. They all look the same. They are all an interlocking ring structure. This is cholesterol. The difference between cholesterol and estrogen, the difference between cholesterol and testosterone, very small. Just the positioning and the shape of these groups attached here. We also use cholesterol as supporting material within the cell membrane, sort of like rebar in concrete, if you will. So it gives the cell membrane the shape it needs to have. You know, like if you are a neuron, your cell membrane has to extend for 4 feet down from your hip to your great toe because you're part of the sciatic nerve. Well, your cell membrane has to extend that long, and so cholesterol is there to reinforce that all the way down from your hip to your great toe, behind your knee and everything. Very, very similar structures. The last category are the eicosanoids. And the eicosanoids they represent some different categories, the most important of which are what we call the prostaglandins. And the prostaglandins are often also considered a hormone. Prostaglandins help to regulate blood pressure and clotting, labor contractions. Most importantly, they help to control the inflammatory response. Now, the inflammatory response occurs if you have a cut or a scratch on your skin anywhere right now. You probably have a red area around that cut or scratch. That's the inflammatory response. It's a good thing. The inflammatory response increases blood flow to the site of an injury. That's why the skin's red. It's warmer. More blood's coming in, brings in more oxygen, brings in more nutrients, it brings in more white cells and takes away waste products and dead and dying cells or cell fragments. So the inflammatory response is part of our healing process, and it is regulated by prostaglandins, which are a type of eicosanoid. So this is very, very important for us. We'll talk a lot more about that in the inflammatory response and when we get into hormones in AP2. So this leads us into proteins, the third category of the organic compounds. Proteins represent a lot of our structures. 30% of our typical cell mass is protein. Proteins do more than any other molecule does. They function both structurally and functionally. They work on structure within the cell. They also operate as hormones and enzymes. And so they can even be contractile. The contractile proteins are what we have in our skeletal muscles, for example, that allow our muscles to contract on command. Just like in the smooth muscle and the cardiac muscle, those muscles are all made of contractile proteins. They're all the same contractile proteins. They have the ability to slide over top each other or shorten or lengthen as necessary. The proteins again with carbon, hydrogen, and oxygen, but now we have nitrogen thrown in. And we may even have sulfur, and we may even have phosphorus in here too, but we'll definitely have nitrogen. The building blocks of a protein are what are called amino acids. And amino acids have an ammonia group and an acid group and some type of functional group. And these amino acids, only 20 of them, but they're held together by what are called peptide bonds. There are only 20 amino acids held together by peptide bonds with an amino group, which is the ammonia end, and an acid group, which is the other end. And in the middle is a functional group. We call that the R group. Only 20 of them. But we can make any protein we need out of this. We're not limited to just 20 amino acids in length. We can have proteins that are hundreds of amino acids in length, probably even thousands of amino acids in length. We repeat them over and over and over again. Consider a typical dictionary. Using the 26 letters of the alphabet, most dictionaries have around 350,000 words just from those 26 letters. How are they arranged? However they need to be. The same with the amino acids and the proteins. You only have 20 amino acids. You can arrange them in any combination to give you the protein that you need. This is what an amino acid looks like. This doesn't change out here. This is the amino group. We call that because it's a derivative of the ammonia group. You know, nitrogen and 2 hydrogens is the basis for ammonia. We call this the amino. And NH4 is ammonia. This has two hydrogens, not 4. Over on the other side is the carboxyl or the acid group. We're not teaching you organic chemistry here, but see, you know, the C double bond O and the OH, that's an acid. It's this part right in here where we have the R group attached. The R is any one of 20 different functional groups. It'll do any one of 20 different things. And whatever that R represents is what the amino acid will become. So there's only 20 amino acids. And it's the presence of this that tells you what it is. Because this is going to always be the same, and this will always be the same. It's what goes on here that determines what the acid's going to be. And these amino acids then are held together by peptide bonds. And you can see there's the amino group there. There's the amino group. There's the amino group there. There's the amino group there. Here's the acid group there. And there's the acid group there. And there's our functional group there and there. Each one, you know, each amino acid is specific for what it's going to do. And so they're all held together by these peptide bonds, one after another, in any sequence, in a very specific sequence. The sequence is already determined by our DNA. Sequence of the amino acids is dictated by our DNA. Consider hemoglobin. Hemoglobin is a protein that's about 360 amino acids long. And the order of those amino acids is very, very specific, dictated by our DNA. You know, when we have sickle cell disease is caused by a substitution of an incorrect amino acid at the number 6 spot. Make the mistake very early in here. The number 6 amino acid in hemoglobin is supposed to be an acid called glutamic acid. Instead, in sickle cell disease, it's valine. And the structure of valine and the structure of glutamic acid are very, very similar. So it's a very small mistake, but it has devastating consequences. By having valine in there, you now have sickle cell disease because the hemoglobin can't carry oxygen properly under stress. And so the hemoglobin becomes brittle and twists and forms a crescent shape, which causes the red cell to assume a crescent shape and reduces its oxygen carrying capacity by about 80%. Plus, because it's brittle, it makes the red cell to have pointy ends and be brittle. Those red cells hurt when they go through capillaries. Because red cells normally are like a water balloon. They slide right through. They're squishy. But now they're not squishy. They're sharp. And they hurt when they go through the capillaries. So all because of one little mistake at the number 6 spot. Out of 360 amino acids, the mistake gets made at the number 6 spot. So, okay. If you're a protein, you have 4 levels of structure. The first level is called the primary level. It is a linear sequence. It's a straight line. If proteins do not occur in straight lines, this is as it's chugging out of the cell itself. The protein has been made and has not yet been twisted into its specific shape. Those proteins all have unique shapes. The shape often dictates what the protein can do. So we go to the secondary shape, secondary structure. We start seeing the protein bending and twisting. We have what's known as the alpha helix and the beta pleated sheet. The alpha helix coils up, looks sort of like a DNA strand, it's like a double helix. It looks like a spring. Hydrogen bonding occurs in the molecule, in the protein molecule, between segments of the primary structure, and that twists it into its predetermined shape. If you're going to be a elastic protein, you're probably going to be an alpha helix. Our hair, because it is, will return to its normal shape, or our earlobes, for example, are elastic. They have lots of alpha helix present in it. The beta pleated sheets that look like an accordion sheet, like an accordion, whatever, we find those where we're going to have great strength. Our collagen fibers that attach muscles to bone are mostly beta pleated sheets in here. And you can have the same structure, same types of either one of these structures in the same protein. And it can be alternating again and again, or it could be the same thing. It depends on where it's going to be located. The tertiary shape is when you have the protein having multiple variations of the secondary structures, the alpha and the beta, alpha and beta. And the quaternary is the biggest of the proteins, and it's essentially 2 tertiaries linked together in here. Hemoglobin is a quaternary protein, meaning it has 4 segments to it linked together in the middle. So up here is the primary structure, the straight line structure, but that doesn't last long. Proteins will move very quickly into their secondary structure with their alpha helix or their pleated sheet type shape. The tertiary structure usually contains both. And then here we see a quaternary structure made up of multiple variations of the tertiary subunits. Let's see what we say here on this. I like how they just drop it at that when they're describing this. But this is the primary structure here with the with each one of these is an amino acid. Now we're normally, as it comes out in a straight line, we start as it's being manufactured in the cell, we start seeing hydrogen bonding occurring from adjacent areas, and that's gonna start twisting the protein around. So we'll see a hydrogen bonding occurring here and here, maybe in here, maybe over here, because the protein has to have a specific shape to do its job. It has to have a very unique shape. Many proteins that are the globular type proteins, the enzymes and the hormones, function very much like a key going into a lock. The protein only works on specific cells where its shape will fit. And so we have to twist the protein around to fit that receptor site on the surface of a cell. Or in the shape of hemoglobin, we twist the hemoglobin protein chain around so that it can carry 4 oxygen atoms. It has an iron atom in the middle of the quaternary structure, and it will carry 4 oxygen atoms. That's what we want. We want it to carry 4 oxygens, but its shape dictates that. Now, so if you're either a fibrous protein or a globular protein. If you're a fibrous protein, you are what we use to make up muscle and collagen fibers and ligaments and tendons. It's not soluble. You're not soluble in water. You're very stable. You're either a tertiary or a quaternary protein. You have great strength. The keratin that waterproofs our skin, the elastic fibers in our ears and in our skin itself are fibrous proteins. Collagen that connects muscles to bone. The most abundant protein in the body is collagen. These are all fibrous proteins. And of course, the contractile proteins of our skeletal muscle, our smooth muscle, and our cardiac muscle are all fibrous proteins. Very powerful. They're contractile. Actin and myosin are the fibers here that we find in our muscle cells. If you are a globular protein, totally different. You are water soluble. You're a glob. It's like a scoop of jelly, if you will. That's what you look like. You're very sensitive to temperature changes and to pH changes. You have very specific regions of activity. We call that your active site, for example. Now, in this animation here, what we're seeing is starch, right? Starch, those are chains of glucose being acted on by an enzyme, a protein called amylase. Amylase will bind to the starch and break it apart into maltose. Maltose, of course, is a double sugar. It's malt sugar. It's related to sucrose. It's used in the baking industry or whatever. But when we eat starch, we start the process of digesting starch. Like you eat a French fry. French fries got starch. The amylase is released in the enzyme. It's released in your saliva, and you start the process of digestion right away in your mouth. And the amylase has an active site on it for these starch molecules, and two parts of it. It'll take two of those individual glucose molecules in starch and break it apart into maltose. And we'll keep doing that until all the starch is broken down to maltose. And then we will continue to break down the maltose later on, as further on in the digestive system. But the amylase is going to break down the large starch molecules into smaller sugar molecules. It only works in our mouth. The amylase has an active site on there that will grab onto 2 of those 6-carbon sugars. And if you are a globular protein, you are antibodies to fight infection. You are hormones. You are what we call molecular chaperones. And most importantly, you are the enzymes. And all enzymes have an active site that unique molecules can land on. In this case, it is a 6-carbon sugar. It has 2 active sites. It has the active sites in there. 2 6-carbon sugars land there as part of the starch molecule. See how it fits together like that. And then we break them apart into maltose. So we convert starch into a simple sugar. The problem with globular proteins is that they can become denatured. They are very sensitive to changes in temperature and changes in pH. Their active site breaks apart. Now, if the temperature change isn't too extreme, if it's reversed and brought back to normal, if the pH change is reversed and brought back to normal, either from too low or too high, then the effects on the active site are temporary. But if they persist, they're permanent. And if an extreme change is irreversible, consider the egg here. The white of the egg is albumin, a very common protein. When you fry an egg, the white, the albumin, becomes denatured and turns white. You know, the yolk stays yellow. It's also cooked too. That's mostly cholesterol. But the white of the egg is albumin, and when it becomes denatured, it turns white, and it cannot be reversed. You can't take an egg and renature it, if you will, and convert it back to its globular state. The active sites are destroyed, and you can't change it. Okay, I'm going to stop here. We'll pick up with enzymes because I don't have enough time left to go through this like I want to. Let me get out of here, and I will post this to YouTube for you today. Anybody have any questions on any of this? We're almost done. We will wrap all this up on Thursday, and we'll start the chapter on cells. Finally done with chapter 2. So, okay, so as I said, we're going to be in lab this afternoon. We're going to be looking at the appendicular skeleton and go from there. So I will see some of you in lab today. Yes, the lab exam does require the lockdown browser. I had a problem with that, which I fixed yesterday. It was supposed to copy over automatically, and it didn't, so I went back and fixed it. So you should be able to get in. Let's see if that was the answer is yes. So, but it should work now. The only thing the lockdown browser doesn't work on is a Chromebook. You have a Chromebook, for whatever reason, Chromebooks and the lockdown browser do not work together. I don't know why. Nobody knows why. So you'll have to use a different computer to get that to work. You'll have to install the lockdown browser on your computer so you can use it. So, okay. Any other questions? That was a good question. So, because if you install the lockdown browser and then try and take the test without the lockdown browser turned on, it'll say, can't do it. So I found that out yesterday. So, okay. I will see you all later on.